Okay, we are getting into the next section of the book, which is part 3, called S2S Modeling and Forecasting. So we're going to get into some specifics of how the system works. And the first chapter in that is called Forecast System Design, Configuration and Complexity by Yuehi Takaya from Japan. I think I'll make it just one podcast to make some of the points which we will return to in subsequent chapters. We looked at this already once from the Earth System Prediction Capability Office of NOAA, and this shows time scales here, essentially forecast lead time going from warnings, alert coordination, watches, and out to climate projections. And on this scale we have decision time scales, so it's kind of a mapping of the forecasts. So we are going from weather time scales of a few days, maybe a week, bordering on to 10 days, and then we have this sub S2S time scale that we have been talking about in terms of weeks 2 to 4, and then season 1 to 3 or 4, let's say, and then out to decades and multi-decades. And there are various sectors that we talked about that require information at certain time scales with certain uncertainty, because it depends on the sector. Reinsurance industry may work with a very different probability of information than agriculture or transportation or airlines, and so on and so forth. This is a broader diagram from the same book from the National Academy of Sciences, talking about the production of calibrated S2S forecasts that involve 3 processes. So we are talking about 3 phases here. Frozen method, quality controlled output suitable for multi-decadal analysis. So we are talking about here observations being assimilated with data assimilation into the model. So we have a coupled Earth system model, and we provide what are called re-analysis. So it's a dynamically interpolated reconstruction of the past climate and Earth system variability. And this is where in phase 2 you have ensemble output useful for S2S analysis. So reanalysis starts there. Forecast system improvement and informing calibration is needed when we do what are called hindcasts or retrospective forecasts, or also called reforecasts. I'm jumping a little bit ahead here, but we'll come back. Essentially, you keep making forecasts year after year, and after a certain period your system, let's say, hasn't changed, and you have some estimate of skill, but you begin to notice that the model has certain biases. For example, it may put MJO always in a certain phase as at the genesis stage. It may be weaker, propagating slower, and so on and so forth. Spatial and temporal biases and uncertainties and errors and so on. So here you recalibrate the system by taking the frozen model, or you do it on the fly where reforecast is done with the forecast. So it's not a unique thing, but you essentially do it for a long period, like let's say 15 to 30 years, where you compute the forecast climatology, if you will, to look at what are the systematic biases in the model, so that you can correct the biases in various ways and calibrate and validate the model in that sense. Okay. On the other hand, operational forecasts require current observations and data analysis to give you analysis for the initial conditions to start operational forecasts. So these two together can give you forecast calibration. Okay, so that's the S2S ensemble forecast here. What are the kind of models that are required? This is just showing an examples of upgrades of the Japanese Meteorological Agency 1-month ensemble prediction system, and you can see that the resolution has increased over time. So we're going here from March 96 to March 2017, and typically these numbers are the truncation of the waves in the spectral representation of the longitude, latitude, space. Obviously that corresponds to a grid size, so gone from 180 kilometers down to 40 kilometers, and the vertical resolution also has gone from 30 levels in the vertical to now 100. Okay, so here are the ensemble sizes. So this is lagged averaged forecast, which means not all the ensembles are initialized at the same time, as we will see in a minute. And so when you lag it, you might have 13 members from a previous time step and 13 members from the current time step. So you have 13 times 2 there, and it's done the same way by increasing the number of ensembles 25 by 2, and here it's somehow 13 times 3 plus 12. So all kinds of combinations of representing the initial condition uncertainty for S2S is done to generate ensembles which represent the number of realizations nature could throw at us, which would represent uncertainty. We have talked about data assimilation before, but here we should mention that initialization includes ensemble Kalman filters, local ensemble Kalman filters, breadth vectors, singular vectors, and this kind of 3D var, 4D var kind of assimilation systems also give you what are called flow dependent initial conditions. So you can see here that in the 4D var, this is 3D var where the system gets fixed at T0 as forecast happens. So this is the previous forecast, whereas in the 4D var there is corrections along the way to optimize the cost function, so you get a corrected forecast. So that's presumably the most accurate one, but it's also very expensive. So initialization is always an issue for designing models for forecast as well. How to decide on ensemble sizes? So this is one way to look at it. This is kind of an idealized experiment where one state of the model is considered reality, and then you keep comparing other realizations with that. So there is a correlation of a single member C1 compared with correlation of ensemble mean CM. So you can see that correlation of the ensemble mean versus single member. There is the single member, which drops off much more rapidly, but as you increase the ensemble sizes to 10, 20, 30, and 40, you can see that the correlation of the ensemble member in this idealized skill metric goes up, but it saturates both in terms of correlation. Of course, will not hit perfection, but you can see that here 20, 30, 40 are beginning to kind of saturate. These spreads here are the ensemble uncertainties or standard deviations of variances, if you will. So one standard deviation range of Gaussian distribution that is fit to the ensemble spread. Okay? Long story short, there is much care needed to figure out what is the ensemble ideal number of ensemble members. May depend on the place, process, season, and so on. So it's not an easy task. This is showing the same thing here, looking at temporal anomaly correlations of weak averaged 2-meter temperature between analysis and 10-member ensemble mean forecasts for lead 14. So 14 days, 14 days minus 15 days, so 14 days is somewhat better, but almost the same. As you go to 16 days, there are more regions where the 14-day has higher correlations. As you go to 18-day, there is much larger degradation. So 14-day is much better in large places than the 18-day forecasts. Okay, so this is for 10 members. So you have to do the number of ensembles and then look for lead times where the skill drops off, like we are doing here. Okay, so all those calculations take time. And this is a table that's showing the configurations of subseasonal prediction systems participating in the S2S project under the World Meteorological Organization, now chaired by the authors of this book that we are using. It's not very easy to synergize or coordinate S2S forecast systems across all centers, because all have different philosophies, different models, different resolutions, different initialization, different ensembling, different data assimilation, and so on. But nonetheless, you have Australia, China, France, Europe, Hadley Setter, I think, from the UK Met Office, Japanese, Korean, US, UK Met Office is down here. HMCR is the Hydrometeorological Center of Russia. Okay, so here are the resolutions that are very different also. You can see CMWF has an incredibly high resolution compared to others in this set, and not all are spectral models, so this is a grid model. This methods of ensembling is either lagged averaged forecast or a burst of forecasts which are all starting from the same time, and we'll see what that means. Ensemble sizes with bursts 3 times 11 and so on. So number of forecasts also differ. So this is doing 13 per 6 hours, 4 per day, 16 per day, and so on. And the start days of the forecasts are different. They all have different philosophies on how best to serve the information. If you serve it on Thursday, it will be better used next week according to the Japanese understanding, and this is doing every day, every 5 days, and so on and so forth. And sometimes there is a synergizing between extended range weather forecast, S2S forecast, and then seasonal outlooks. Seasonal outlooks may be done every 10 days or every month, and so on and so forth. And there are different periods. Okay, so the reforecast ensembling is also done on the fly, which means reforecast and forecast are done at the same time, whereas these are doing with a fixed system. So they go back in time and do hindcasts with a fixed system for 15 to 30 years to derive model parameters like climatologies to understand the biases in the forecast system. Ensembling, to revisit, this is from the Met Office. We had seen how initial conditions are generated to represent the uncertainty compared to the Mother Nature, which gives one deterministic realization, let's say, and you want to cover the potential range of paths Mother Nature could have taken by representing this. So this is where bread vectors, singular vectors, ensemble Kalman filters, 4D var, etc. go in terms of methods. So this is the climatology the model has, and then the forecast uncertainty is there. So skill metrics take care of whether you are capturing the deviations from climatology accurately or not. Okay. Briefly, this is the burst ensembling, where every ensemble members starts at the same time. This is the lagged average forecasting. Obviously, if you start from a previous time and the forecast is starting here, the skill would have degraded, but there are other advantages to doing this way. For example, the computational power required to do this is much better than this, but there are disadvantages that you are mixing lower skill forecasts with better skill forecasts. So this initialization may have a better skill than initialized earlier, forecasts initialized earlier. Okay, so these are the choices to be made. How do you compare them? So this is a figure that shows that equivalent ensemble sizes of a burst forecast system and the lagged average forecasting system can be seen here. Not very easy to understand, unfortunately, but again, we are comparing with single member correlation with lag 1 with sizes of LAF and bursts, where 2 sets of 20-member ensembles are used either as a 40-member ensemble for burst forecasting, or 2 20-member ensembles for lagged average forecasting. And Without struggling to explain this, we know that as ensemble size goes up, skill goes up compared to the single member correlation, but depends on the intrinsic skill. If it's low, then ensembling is not going to help. If it's high, ensembling will help to increase the skill. But the main message here is that a 30-member ensemble of a burst forecast system seems to do as well as a 40-member ensemble of a lagged average forecast system, but computational efficiency and other details can be different in this case. Okay, so we kind of ran through this, but we will revisit many of the issues. So model configurations, resolutions, data assimilation systems, initializations, reforecasting systems are all the issues to be considered when you want to worry about forecast system design. Okay.